Hi, I'm Ron Covell. I've been a professional metal fabricator for over 40 years, and over that time I've done a lot of different work. I worked on race cars, street rods, custom motorcycles, custom furniture, and sculpture. TIG welding was developed in the 1940s, mostly to serve the needs of the aircraft industry, where they needed to weld aluminum and magnesium. Initially, helium was used as the shielding gas. That's where the term heliarc welding comes from. Nowadays, it's more commonly called TIG welding. TIG stands for tungsten inert gas. Technically, it's called GTAW welding. That stands for gas tungsten arc welding, but you'll find that TIG welding is the most popular term today. A lot of the work that I do is body work on cars and bikes, and the TIG welding process is ideal for this. Now, many people use MIG welding for body work, and while it's strong and it's fast, there is a major limitation, and that is that the weld bead is brittle. So if you do very much hammering on a MIG weld bead, it's liable to fracture. The TIG weld bead is considerably softer, and I can hammer on it quite a bit with no fear of it cracking. Let's talk now about the safety aspects specific to TIG welding. Most of the safety issues with TIG welding have to do with protecting my body from heat and light. The light given off by an electric arc can cause the sunburn from hell, so it's essential that I protect my body from those harmful rays. I wear gloves when I'm welding, and I like these particular gloves because they're made of a very soft, flexible leather. That's a very nice feature. It's important that I wear a long sleeve shirt when I'm welding. This protects my forearms from both light and from any occasional sparks that may be thrown off. The fabric of the sleeves is important. What you don't want is a synthetic fabric, because if anything hot comes in contact with it, it melts, it sticks to your skin, it's really a mess. So cotton is probably the best fabric, and a tightly woven fabric is the best. It's important that I have foot coverage as well. I'm wearing leather shoes. You don't want to wear sandals when you're TIG welding, and in fact open-toed shoes or canvas shoes are not to be recommended either. It's essential to use a welding helmet when you're welding. And this one I like for a number of reasons. The first is because it has a very large window. I wear bifocals, and to focus close I need to look through just the bottom quadrant of the lenses. Only a helmet with a large window allows me to do that. This is an auto darken helmet, which means that it's a very light shade when I'm not welding, and as soon as the arc starts, it goes to the dark shade. So it protects me from the welding. And in addition, this welding helmet has a dial that allows me to control the shade of the lens. For welding light materials, I usually have it set on a shade 9. When I'm welding heavier materials, I need to use more current. It makes a brighter arc. I may need to darken it to a 10 or even an 11. So it's nice to have that adjustment. So those are the basic safety issues. Let's take a look now at the machine setup. This is the machine we'll be using for our demonstration. It's the Miller Dynasty 200DX. Really a nice little machine. Don't let the small size deceive you. This is an industrial strength machine. It's a full-on 200 amp machine. It can work either AC or DC. The inverter technology allows us to have advanced controls of the waveform that we'll talk about shortly. But one of the things I really like about this machine is its portability. It only weighs 45 pounds. That means I can pick it up and take it anywhere. It plugs into anything between 115 volts, 440 volts, so we can use this machine anywhere that electrical power is available. This is the handpiece. This is where the heat comes from. There's a tungsten electrode, and the arc stream comes off of this tungsten electrode. Now there are two basic processes that TIG welding is done with: AC and DC, alternating current and direct current. In direct current, electrode negative, which used to be called straight polarity, the direction of electron flow is from the electrode into the workpiece. So the majority of the heat goes into the workpiece. The handpiece stays relatively cool. A few metals are welded in the alternating current mode. Aluminum and magnesium are the most common metals welded this way. In the alternating current mode, The current goes part of the time from the electrode to the workpiece and part of the time from the workpiece to the electrode. In the old sine wave style machines, the amount of time spent on each mode was equal. With the advanced inverter technology, now we can control how much of the waveform is in electrode negative and how much is in electrode positive. And what we're really changing with that is the balance between penetration and the cleaning action of the arc. Very nice to have that control. Let's take a look now at how the actual settings are made on this machine. All of the controls on this machine are done with push buttons. The main power switch for this machine is on the back, and once it's switched on, you can see the display on the front. The first switch we'll look at is polarity. This is where we switch between alternating current, such as we'd use for welding aluminum, and direct current, which we'd use for most everything else. The next switch is for the process. For all of the TIG welding I do, I use the top setting, the TIG high frequency impulse setting. What this means is that the arc will start if we just get the electrode close to the metal and push down on the foot pedal. That means we don't need to touch the electrode to the base metal, which could possibly contaminate it. There is a setting for lift arc, which means you would touch the electrode, but I don't recommend using that for TIG welding. And there is a setting for stick welding. Actually, this makes a very good power source for stick welding. The next button is the output control. This might be used if you ever weld without a variable hand or foot control. Mostly I keep this disabled in the standard position. The next button we'll look at is for the pulse portion of the circuitry. What this does is it sets a lower limit and an upper limit for the current, and then when you're welding, the current cycles automatically between the limits that you set. This does have some applications for certain types of welding. The next button is for sequence. Again, if you're using a foot or hand control, this is disabled. The next button is used to set pre-flow and post-flow. Now, pre-flow I'm going to do in a manual manner, so we don't need to use the automatic setting for pre-flow. Post-flow is different. What we're setting with post-flow is the amount of time that gas continues to flow over the electrode, shielding it as it cools down after the welding current has stopped. Without any post-flow, the electrode oxidizes immediately, and then the next time you weld, the oxides break off the electrode and they contaminate the weld pool. This is very bad. So we need to have enough post-flow to shield that glowing red electrode until it cools enough that it won't oxidize. A pretty good rule of thumb for this is that we need about 1 second of post-flow for every 10 amps of welding current. So if we're welding at 100 amps, we want at least 10 seconds of post-flow. The button on the right is the one that controls the AC waveform. This is the control we have that balances cleaning versus penetration. And in the other mode, we can change the frequency of the waveform. The older sine wave welders always had a 60 cycle per second waveform. With this machine, we can control all the way from 30 cycles per second to 250 cycles per second, and the higher frequencies develop more penetration. Probably the most important control we have is the amperage of the welding current. We can set it from a low of 5 amps all the way up to 200 amps. The more amperage, the more heat. And this window shows the output voltage. You won't see anything in this window until we're actually welding. TIG welding relies on the use of an inert gas for shielding the weld area. In most cases, we use argon gas, and that's what's in this cylinder. For certain specialized situations in industry, helium gas can be used, or sometimes an argon-helium blend. That promotes greater penetration in thick aluminum plate. But for everyday use, argon is what we'll use. There's a high-pressure bottle with the argon in it, and there's a valve on the bottle that needs to be opened. You need to use care when opening this valve. You should open it very slowly so the gas doesn't rush in against the diaphragms in the flow meter. And then it's opened until it seats against the top seal. If you only open this a small amount, it can leak gas out around the stem. And once you bought a couple of bottles of argon, you'll appreciate just how expensive the gas is. And then the pressure is set by turning this adjustment on the flow meter. And for most welding, we want between 15 and 20 cubic feet per hour. You must be very careful when handling these bottles. If the bottle accidentally gets knocked over or if the stem is broken, this bottle will take off like a rocket. So here's a simulation of what would happen if the neck gets broken on a bottle. Not a pretty picture. There's a few more components of the machine I want to talk about. This is the foot pedal that I normally use to start the machine and then control the heat as I'm welding. So when there's no pressure, there's no current flowing. And when I just press this down a little bit, it starts the current flowing, but at a very low amperage. And then as I press the pedal down farther and farther, it builds the heat up as much as I want to or need to. Very nice to have that kind of control. And I use this foot control for most of the welding I do. Occasionally, for out-of-position welding, it's not convenient for me to use a foot pedal. Imagine if I'm laying on my back or working on a ladder. So in situations like that, there's an optional heat control that goes right on the TIG torch. So this has a small thumb wheel that can be turned, and this does exactly the same thing as what the foot pedal does. When it's rotated one direction, the machine is switched off. Rotating it the other direction just a tiny bit switches the current on, but at a low amperage. And then the more I rotate this, the more it builds up the heat at the weld. And then I can switch it off immediately. Very nice to have that as an optional control. And of course, any time that I'm doing welding, the workpiece needs to be electrically grounded. And that's normally done with a clamp like this that connects directly to the machine. Let's take a look at some different types of TIG torches. This is an air-cooled torch. The real nice feature about this is the machine doesn't need to have a water recirculation system, so it makes the whole thing more portable. But you can see the disadvantage is this complete torch is just a little bit larger than a water-cooled torch. So the advantage of the water-cooled torch is that it's a little easier to manipulate. But if you're using a water-cooled torch, then you need to have 3 hoses, one for water in, one for water out, and one for the argon shielding gas. And you need to have a recirculating pump that is close to the torch. So advantages both ways. The cup size is a little bit larger on the air-cooled torch, a little bit smaller on the water-cooled torch. So you can get into tighter areas with the water-cooled torch. There are different size caps that go on this torch. This is the longest one. There's a medium one for this torch, just like the medium one on this torch. And then there's a very short button cap as well. And then this is a completely different type of torch. This has a lot of sort of advanced features. You can see that the nose piece that's on it now sticks straight out. So this enables you to get into tight recesses for welding. Another feature this torch has is that the body is designed to be flexible. So you can kind of get in over obstacles and into corners with it. So that's a very nice feature. And the really neat feature about this particular torch is that the end piece is replaceable. And there's a wide range of options that can be put onto the end of this. Let's get the straight end taken off. It just unscrews. And then we'll put on an angle tip, which is very similar to the angle tip on our other torches on the table. And this one has the short end cap. And there's a different angle that can go on it as well. This has no back cap, so this can go into a very, very tightly constricted areas. So this is kind of an unusual torch, but it has some nice features. If you're doing a lot of really technical work, it might be worthwhile investing in a torch like this. One more thing to mention, each of these cups has a ceramic nose piece on it. You can see that each is a different size. What's going on with the size is you need an orifice large enough to pass enough gas so that it completely shields the weld area. But the larger the opening, the more difficult it is to get into constricted areas. So that's why the smaller cups are made as well. And what I have on this torch is a special cup that's called a gas lens. And what goes behind the ceramic cup is a special collet body, and the collet body has a couple of screens in it. The function of these screens is it smooths out the flow of gas going through the ceramic cup. it changes it from a somewhat turbulent flow into laminar flow or straight line flow. And one of the advantages of using a gas lens is it does give you better gas coverage of the weld area, but also you can stick the tungsten out a little bit farther if you need to. If we stuck the tungsten out this far with a traditional cup, it wouldn't work. We wouldn't have a sufficient shield around the tungsten to do good welding. So those are some of the varieties that are available with TIG torches. Next thing we'll do is talk about the bewildering array of tungstens that are available for the torch. I should probably start by explaining why the electrode is made of tungsten. Tungsten has the highest melting point of any metal, and it retains its hardness even at red heat. It's also a good electrical conductor. These factors make it ideal as a TIG electrode, but pure tungsten is not used as often as tungsten alloyed with other materials. Tungsten electrodes can be alloyed with oxides of thorium, cerium, lanthanum, or zirconium, and in percentages of 1%, 1.5%, and 2%. Further, they're available in different diameters, from 0.010 of an inch to 1/4 of an inch, and they're available in several different lengths. It's no wonder that people get confused about electrode selection. For the old sine wave welders, which have been pretty much superseded by square wave and advanced square wave inverter machines, pure tungsten was often used to weld aluminum in the alternating current mode. All tungsten electrodes are color-coded on one end to indicate the type, and pure tungsten electrodes are color-coded green. Thorium has been used for years to improve the arc performance characteristics of tungsten electrode for direct current welding. Although thoriated electrodes are still used, concerns are mounting about the health and environmental risks of thorium since it is a radioactive material. 2% thoriated electrodes, the most popular type, are color-coded red. Modern welding machines can make better use of the new rare earth tungstens, ceriated, lanthanated, and zirconiated, none of which have any radioactivity at all. Ceriated tungsten can be used for both AC and DC welding, and it has better arc stability and better current carrying capacity than thoriated electrodes. Ceriated electrodes are color-coded orange. It's a good general-purpose electrode, and these are one of my favorites. Lanthanated tungsten can also be used for either AC or DC welding. Lanthanum increases the current carrying capacity of tungsten by 50%, and it is highly resistant to weld contamination. 1.5% lanthanated tungsten, the most popular percentage, is color-coded gold. This is another good choice for general-purpose welding. Zirconiated tungsten is used for AC applications only, and especially for sensitive work where the slightest inclusion of the electrode in the weld bead would cause problems. It produces an extremely stable arc. Zirconiated electrodes are color-coded brown. Once you've chosen the proper type of tungsten electrode, the next step is to choose the diameter. 40 thousandths is about the smallest that I use, and I use 3/32 for more general purpose work. Occasionally, for work pieces that require a great deal of current, I might bump it up to 1/8 inch diameter. A little experimentation will quickly tell you if your tungsten is too small, since you'll see the tip melting. 7 inches is the standard length that tungsten electrodes come in. But note that to use the full length, you have to use the longest end cap for the TIG torch. Now for bench welding, that's no limitation, but if you ever need to get into a tight area, that could be limiting. If you cut the 7-inch tungsten exactly in half, you get two pieces 3.5 inches, and that's exactly the right length to fit the medium-size end cap. And you'll have to cut the tungsten a little bit shorter to use the smallest end cap. It's best to sand or grind through the tungsten to shorten it. They can shatter if you try and break them. Or even if they don't shatter, it can split the grain of the material, which causes problems with the arc later on. Remember, they're only color-coded on one end, so if you cut them in half, one part will be unmarked. Now let's talk about proper electrode preparation. The tungsten electrode is pointed by sanding or by grinding. For very sensitive work that must pass X-ray testing, it is recommended to use a dedicated belt or wheel used for tungsten electrodes only. If you're not doing sensitive mil-spec work, you don't need to be quite so fussy on this point. If it's a pretty long tungsten, I can hold it in my fingers and rotate it at a steady rate to sand the tip. If the electrode is short, it's better to hold it in a pin vise. Another very convenient way to point electrodes is to use a cordless electric drill. I like to sand an angle on the tungsten at about the same angle that a pencil sharpener puts on a pencil. Another way to say this is that the length of the sanded area should be about 2.5 times the electrode diameter. All of the sanding or grinding scratches should go along the length of the electrode, which means that you must hold it in line with the belt or wheel as you're pointing. If the sanding scratches spiral, the arc coming off the electrode will not be as stable. For welding thin stock at low amperage, a needle-sharp electrode really helps to focus the arc tightly. For high current work, having a tiny flat on the tip of the electrode will help keep bits of tungsten from spitting into the weld bead, causing contamination. For anyone using pure tungsten in a non-inverter machine, the proper preparation is to put a ball on the end of the tungsten by running a burst of DC positive current through the electrode. There are dozens of different welding rods available, many more than we can cover in a short program like this. The problem is that it's hard to tell what the alloy is just by looking at the rod. For example, I have 3 pieces of rod here. One is 1100, one is 4043, one is 5356, and you can't tell the difference by looking at them. So it's important that you store your filler rod in such a way that you know what alloy you're using. Fortunately, there are some good resources to help you with proper filler rod selection. I'd suggest starting with your local welding store. Also, there are some good books on welding that cover filler rod selection. And now there are some wonderful online resources that help with that as well. But for every welding job you undertake, you must research the proper filler rod and use it. Using the wrong rod can lead to disaster. The last thing a good welder wants is for one of his or her welds to fail in service. Anytime you weld metal, one of the first things to think about is cleanliness. It's essential. And I have a variety of pieces on the table here that show different types of contamination. Any oil or grease that's on the surface of material needs to be cleaned off. You cannot weld through oil or grease. Any paint that's on the surface needs to be cleaned off. Again, you can't weld through paint. Anything that's galvanized needs to be stripped down to bare metal. What makes galvanized metal galvanized is a coating of zinc on the surface. When zinc is heated, it gives off a fume that's poisonous. So it's very important to strip any galvanized material before heating or before welding. Hot rolled steel has a scale on the surface, and that scale has to be stripped before it can be welded. Any metal with rust on it needs to be cleaned. You can't make a good weld through rust. Any corrosion on the surface of metal will prevent the puddle from flowing well, so it's very important to clean off corrosion. Metal that has plating or anodizing on it must be stripped before it can be welded. And this can be tricky because sometimes the plating is a lot like the color of the metal underneath it. For example, the part I'm holding is clear anodized aluminum. It's pretty much the same color as bare aluminum, but unless we clean this anodization off the surface, we won't be able to weld this metal very successfully. So regardless of the surface contamination, it must be cleaned before we can do the welding process. And there's a variety of different ways to clean metal. I'll show you just a couple that I use. One of the best ways to get grease or oil off of metal is to use a solvent. I'm going to be using acetone. It's a pretty strong solvent, but it's very effective. But you do need to use safety precautions. So I have safety goggles on and rubber gloves. So you can see there's a big pile of oil right on the end of this metal. And I'm going to just put some acetone on a cloth. And then I can use this to get that greasy film off of the steel in preparation for welding. Okay, so that's done a very nice job. So that's using a solvent to strip off oil or grease. Very often you can use abrasives to clean metal. If there's only light rust or corrosion on the metal, sometimes a wire brush is sufficient to take it off. But if there's significant rusting or corrosion, we need to use a more aggressive abrasive. One of my favorite abrasives is a strip and clean wheel, and this will easily take off even the scale that's on hot rolled steel, as well as any corrosion that might be on aluminum. It's really important to use the proper safety gear with this because it will throw off little particles as it's spinning. So I'll be using a full face shield, hearing protection, and gloves. Let's get started on this piece of hot rolled steel. So you can see that does a very effective job stripping off the scale on hot rolled steel. This strip and clean disc is much more effective than sandpaper for work like this. Okay, now let's strip the corrosion off of the aluminum plate. Okay, so you can see just how fast this strip and clean disc works. It's my favorite for taking off heavy corrosion or hot rolled scale or rust from metal. We're going to take a look at an interesting way to strip either rust or galvanizing off of steel. This is muriatic acid. It's a highly corrosive material and it really needs to be handled with care. You'll notice I'm wearing safety goggles. This is essential. And I have rubber gloves on. You really don't want to get this on your skin. In real life, I would not do this stripping indoors. I'd go outdoors because I've learned that the fumes given off by this acid will rust any bare metal surface. So you really want to do it outdoors. But for our demonstration, I'm going to dip first a rusty piece of metal in some acid and then a piece of galvanized steel. And you'll be able to see just how quickly it strips them down to bare metal. So let's do the steel piece first. This can work fairly quickly, but it depends on how rusty the part is. Our test piece has only a light coating of rust, so it should strip that off in just a few seconds. If the rust is very heavy, it might take a couple of minutes for this. And I'll neutralize this acid by dipping the part in water. And now let's do the galvanized piece. And you'll see the zinc starting to boil off the piece as soon as it goes into the acid. And this is where it's really giving off those toxic fumes. So again, I really recommend that you go outdoors to do stripping of this type. And again, I want to neutralize the acid by dipping it in water. So you can see that in just a few seconds, I've been able to strip both of these pieces. And they could be stripped with abrasives, but this is a much faster process. When you're welding, posture is very important. I can't weld well at all if I'm standing with my body totally unsupported. I just don't have sufficient control over the position of the torch. At the very least, I want to plant my hip or my shoulder against something stationary. That way, at least the upper part of my body is positioned well. What I really like to do whenever I can, though, is to be seated when I'm welding. That gives me much better support. And even when I'm seated, it really helps a lot if I can plant my elbows on the table. That way my forearms are positioned solidly at my elbow, and I have very fine control of my hand position. But what's even better than that is if I can rest my forearms or the base of my palms either on the edge of the table or on the workpiece. That gives me the finest control over the position of the torch body and the welding rod. One more point I'd like to make. You can see I have a small holder here. It goes on the edge of the table or the edge of the workpiece. This is a very handy device, and you might consider making one for yourself. This is one I simply made from a C-clamp with a loop of wire on the end. Very handy device. I think the best way to learn how to TIG weld is just to put down beads on a flat piece of metal without adding any filler rod. So this is a piece of 60 thousandths mild steel, and we'll run some beads on it. Now I have the machine set up already. It's set to DC electrode negative. It's set to 75 amps. The high frequency is set to impulse start. We're using the foot control as the remote. The pulse is disabled. The sequence is disabled. And I have it set to 10 seconds of post flow and 17 cubic feet per hour of argon flow. I have the torch set up with a 1/16 2% serrated tungsten, and I have the tungsten sticking out about 1/8 of an inch. Notice that I'm putting this on a piece of copper. There's a good reason for this. If I'm welding steel and I'm on a steel table, if I get full penetration, it's going to stick my workpiece to the table. Pretty hard to break it loose once you've done that. A piece of copper or even aluminum under the workpiece prevents it from sticking. So let's talk now about the torch positioning. First, hold the torch vertical and then angle it 10 or 20 degrees in the direction of travel. We're going to be moving the torch in this direction once we start welding. Then the next step is to get the proper gap between the tungsten electrode and the workpiece. It should be just about 1/16 of an inch. Then I tap the foot pedal to get the argon gas flowing. This is very important. This pre-flow will get any moisture out of the gas line that comes to the torch. That kind of moisture could cause weld contamination. And it also makes sure that the tungsten electrode is shielded with gas when the arc starts. Once I have the pre-flow going, then I start pushing the pedal down to start the arc. And as I push the pedal down more and more, a puddle will form. Once the puddle is formed to the proper size, then I start moving the torch very slowly toward the other side of the plate. It's very important that I move the torch smoothly and evenly. Very important that I maintain this 10, 15, or 20 degree angle. Once I'm approaching the end of the weld, I stop moving the torch and I start backing off on the foot pedal. Once the foot pedal reaches the top, the arc will stop, but the gas will continue to flow because we have 10 seconds of post flow programmed into the machine. It's very important that I keep the torch in place, flooding the hot base metal and the tungsten electrode with shielding gas until that post flow stops. Then I can take the torch away. Okay, let's get started. Your goal with running a bead is to keep the width of the puddle uniform. The faster you go, the narrower the bead will be. The more heat you apply, the wider the bead will be. Often, as the part you are welding builds up heat, you'll have to either let up on the foot pedal or move the torch faster to keep the width of the weld bead uniform. Okay, when I release the foot pedal, the arc is extinguished, but the gas will continue to flow for that 10-second post flow we have set on the machine. Once the post flow stops, then we can safely pull the torch away. And there's our first test bead. Let me tip this up so you can have a nice close look. And I think it looks pretty darn good. Now I'd encourage you to make dozens and dozens and dozens of beads just like this without adding filler rod, because it's a great way to get the feel of the hand motion, the foot pedal, and everything about the TIG welding process. Once you're really comfortable laying down beads with no filler rod, then you can start adding rod. Okay, so I've cleaned the next piece we're going to weld on, and this time I'm adding filler rod. This is 1/16 inch diameter ER70S2 welding rod. The machine settings are the same. Just like before, we'll hold the torch at a 15 degree angle in the direction of motion. I'm going to hold the rod at about a 15-degree angle from the base metal. So you'll see the angle between the rod and the torch is just about 90 degrees. We'll get a little pre-flow going from the torch and then start the weld. When adding filler rod, I'm not shooting for the center of the puddle. It's better to just touch the filler rod to the leading edge of the puddle. The puddle will draw in the proper amount of rod. You don't have to stuff a lot of rod into the puddle. When withdrawing the rod, be sure not to pull it back too far. You want to keep the hot end of the rod inside the envelope of the shielding gas. You should be watching the edges of the weld bead too. The edges should flow nicely into the base metal. If you're welding too fast or too cold, the bead will stand up above the metal without blending in very well. If you're welding too hot or too slow, the weld will flatten out and lose definition, and you'll probably get more bleed through on the backside than is desirable. As you approach the end of the weld, start diminishing the heat with the foot pedal and add smaller amounts of rod. Okay, so I backed off on the pedal, and I'm leaving the torch in place until the post-flow of argon gas stops. That way both the tungsten and the base metal will be shielded. Okay, so let's take a look at our weld bead. Looks pretty decent. What we're looking for here is uniformity of height and uniformity of width. And I think it looks real nice. So again, I'd recommend that you practice running a puddle and dipping rod in it quite a bit before it's actually time to weld a joint. So the next demonstration I'll do is putting two pieces of metal together, running a bead, and adding filler rod. Okay, now we're ready to weld two pieces together. So this is the same material. It's 16 gauge cold rolled steel sheet, so the settings on the machine remain the same. And the first thing I'm going to do is just to put these parts together and put small tack welds spaced about every inch. This will hold the parts in perfect alignment as we do the finish welding. Although I never want to touch the cup to the metal when welding, it really helps to plant the cup against the metal so I have a point of contact to rock from when tack welding. Okay, so we have the parts tack welded together now. Now I'll clean the joint in preparation for welding. Okay, and just like before, I'll start the puddle right on the edge of the joint and then dip the rod into the puddle and follow that puddle across the joint until I reach the far end. Again, you're watching a lot of things when running a weld bead. You're probably going to need to make small changes to the heat as you go, or change the speed you're moving to keep the weld bead a constant size. You want the sides of the bead to flow in nicely with the base metal, and you want a uniform ripple pattern to form on the top of the bead. As you near the end of the weld, start decreasing the heat with the foot pedal and add smaller amounts of filler rod. The last dab of rod should be placed just before the arc is extinguished. Okay, I'll keep the torch in place until the weld cools. And we'll take a look. So we're looking for a weld with uniform width, uniform ripples in the weld bead, and we want to be sure that we do have full penetration. And we do. For the next demonstration, we're going to weld stainless steel. I have two pieces of stainless here, 1/8 inch thick, and they're put together into a T configuration. I'll get this clamped down to my table so it doesn't move as I'm starting to add filler rod to it. Okay, let's talk about the torch angle next. The torch should be angled halfway between the horizontal portion of the T and the vertical portion. So I want about a 45-degree angle in this direction. And then also I want that 15-degree angle off of vertical pointed in the direction of travel. The filler rod I'm using is 1/16 diameter, 308 stainless rod. Now normally I would weld the side of this that faces me. Today I'm welding the side that faces the camera so you can have a better view. So I'll tap the foot pedal to get the pre-flow of argon gas going, then I'll start the arc, start feeding the rod into the puddle, and move that puddle very slowly and evenly toward the opposite end. Okay, and as always, I'll keep the torch in place, flooding the base metal and the tungsten electrode with shielding gas to prevent them from oxidizing. I forgot to mention that the alloy I'm welding is 304 stainless, which is far and away the most common alloy. That's why I chose the 308 filler rod. But let's take a close look at the weld itself. Stainless welds beautifully. It flows like water. And typically a weld made on stainless will have a finer and more uniform bead pattern than any other material. So I have a piece of 2-inch square steel bar on my table and a piece of 35,000 steel sheet. And I can easily join them together. The filler rod I'm using is 35,000 ER70S2. I'm going to put one tack weld right in the center, and then I'll weld this joint. Okay, so we have those pieces joined together. Let's take a close look at that. So even though there's a huge difference in the thickness of these materials, using the TIG process, we can make a tiny, delicate little fillet weld to join them together. The next piece we're going to run a bead on is a piece of aluminum. This is 1/16 inch thickness, 3003 aluminum sheet. And just like we did with the steel, I'm going to run a puddle across the panel. Real good way to practice your technique of TIG welding aluminum. Because we're welding aluminum, I've set the machine a little differently. It's on alternating current. The amperage is set to 90. I've set the frequency to 120 cycles per second. That's a pretty good all-around setting for aluminum. I've set the balance to 75%, quite a bit stronger toward penetration because we don't need very much cleaning on fresh aluminum like this. The argon flow is set to 18 cubic feet per hour, and I have 10 seconds of post-flow set. I've gone to a larger tungsten. We need to have larger tungsten because we're flowing more current for the aluminum. So it's a 3/32 diameter tungsten, it's 2% serrated, and it's sharpened to a very fine point. So just like we did with the steel, we're going to get some pre-flow going by bumping the pedal. Then I'll hold the torch at about a 15-degree angle off the vertical, start the pedal, and just move it slowly across the panel. Okay, I'll keep the torch in place while the 10 seconds of post-flow continues. That's going to protect the tungsten and protect the base metal. And now let's tip this up and take a close look. What I'm looking for is uniformity of the width of the bead that I've run and the uniformity of the ripple pattern. And it looks quite good. So I'd really encourage you to do this dozens of times if you're just learning TIG welding. Just run a bead across a panel without adding filler rod. It's a great way to build up your coordination or to feel comfortable with the process. Once you get good at doing this, you can get on to the next step, which is adding filler rod. Okay, now we're going to run a bead and add filler rod. The machine settings are the same tungsten setup. The filler rod I'm using is 1/16 diameter, 1100 filler rod. So again, I'll get some pre-flow going with the torch, hold the torch at about a 15-degree off the vertical, and hold the rod at about a 15-degree angle off the work. So the angle between the rod and the torch is just about 90 degrees. Here we go. Okay, I'll keep the torch in place until the post-flow stops. Then we'll tip it up and take a look. And by gosh, looks like we have a nice, uniform, consistent weld bead. Okay, so once you get comfortable adding filler rod when running a puddle across a plate, then you're ready to start welding an actual seam. So that's what we'll do next. So I've just cleaned both edges of the plates to be joined, and it's the same material, 60 thousandths 3003 aluminum. So I'll place them tightly together on my copper backing. I'm going to put a tack weld near this end and then a couple more tack welds along the joint before it's welded. Okay, now I'm ready to make the weld. Now aluminum has some special considerations. As I approach the end of the weld, I have to do things a little bit more carefully. First of all, I'm going to get off the heat rather slowly, and and I'll be adding filler rod as the puddle diminishes in size. And then just before the arc is extinguished, I dip the rod one last time and then ease off the foot pedal. The result of this is that I can eliminate a shrink crater, which I would otherwise have at the end of the weld. And a shrink crater is an easy place for a crack to start. So this technique of slowly bringing the heat down and adding filler rod right up to the last minute is really crucial on aluminum. So let's get some pre-flow going and we'll start the weld. Okay, and I'll keep the torch in place until the post-flow stops. Then we'll lift it up and take a look at how we did. So it looks like the weld bead is really quite uniform. The space between the ripples is very even. And it's a nice low-profile weld bead. Let's flip it around and see what kind of penetration we got. And the penetration is excellent. There's always been a mystique about welding aluminum. You certainly need to practice to become proficient with it, but I don't think it's any more difficult to weld than the other metals. I brought in a different welding machine for the rest of the demonstrations. This is the Miller Dynasty 300DX. This is a 300 amp machine, whereas the 200DX is a 200 amp machine. So this is a better choice for welding thick aluminum pieces or anything that requires a high current output. It's got 100 amps more output than the machine we've used previously. The control panel on this machine is nearly identical to the controls on the 200DX. The push buttons control the same factors, they're in the same place, they work the same way. Another difference with this machine is that it's equipped with a water-cooled torch. Now the air-cooled torch is a good unit. It's good for power output around 130, 140, maybe 150 amps for intermittent use. But if you're welding continuously at high amperage rates, the handpiece of the air-cooled torch does tend to build up heat. The water-cooled torch stays much cooler, so that's an advantage for welding thick materials. Another nice thing about this unit, the TIG runner, is that it comes with a water recirculation unit mounted to the same cart that the welder is attached to. That gives you a lot of portability. This whole unit can be moved around the shop. It's only tethered to the wall with a single power cord. Very nice feature. So the next demonstration we're going to do is making a lap joint on 3/16 aluminum plate. For our lap joint demonstration, I'm going to be welding 3/16 inch thick 6061 T6 aluminum plate, and each piece is 2 inches wide. So I'm going to place one piece over the other. I'm going to use a small C-clamp to hold them into position. And the C-clamp does two things. It keeps them from moving as I'm doing the tack welding and finish welding. It also is going to electrically ground the parts, which is important. And I have a dedicated brush that I use for aluminum. I'm going to use that to clean the joint. And I'm going to put one tack weld on this corner and then start the weld from the other side. The welding rod I'm using is 1/8 inch diameter 5356 rod. That's the best match for the 6061 T6 base metal. Okay, I'll unclamp this and tip it up so you can have a nice close look. So here's our lap joint on 3/16 aluminum plate. I think it came out real nice. The machine settings I used for this joint were the same as for the previous aluminum demonstration, except that I bumped up the current to 200 amps. Everything else is the same. The next joint configuration I'm going to weld is a corner joint. The material is 90 thousandths 3003H14 aluminum, and you can see that I've used an angle on the inside to position the pieces in the proper orientation, and I've used C-clamps to hold all the parts together. So I'm going to put this right side up, and I'll use my dedicated aluminum wire brush to clean the joint. And the next step is I'll put a tack weld on this end, a couple of tacks in the middle, and then a tack weld on this end. After that's done, then I can remove the clamps and get set up to weld the seam completely. Okay, I'll pull the clamps off. Give it a quick wire brushing. And we're ready to weld that joint now. Okay, so there is our completed corner joint. The corner joint is actually one of the easiest joint configurations to weld. For the next demonstration, I'm going to be welding some copper sheet. This is 1/16 inch thick copper. I have two pieces here, and I bent up a 5/8 inch flange on each piece. I'm using an angle plate on my table to hold each piece in proper alignment for welding. Now, it was a revelation for me when I first learned that copper could be TIG welded. For years, I'd welded more common metals, such as mild steel, stainless steel, aluminum, and even some magnesium, and it never dawned on me that copper could be TIG welded. So the first time I wanted to try it, I didn't know where to get the proper filler rod, so I got some electrical wire, stripped the insulation off of that, and used it for filler rod. It actually worked. I was able to form a puddle and add the rod to it and make a weld bead, but I got a bead with a lot of porosity in it. Later on, I learned that there's a special deoxidized copper rod designed for TIG welding. You can get that from many welding stores, or they can special order it. And using that rod solves the problem. Then you can flow a puddle that has no porosity. So it's a real nice clean process. So let me clean this joint in preparation for welding. One more thing to mention, one limitation for welding copper is that copper is a tremendous conductor for heat. So it takes a lot more heat input to form a puddle than with any other metal. So that means you just have to crank up the amperage on the machine, and once you've done that, you can successfully weld copper. So I'm going to form a puddle and start dipping the rod into it, and we'll join these pieces. Okay, then we'll rotate this piece so I can reach the other portion. Copper is welded with direct current electrode negative, just like most other metals. So I think you can see that the copper flows beautifully once you get it up to temperature. It's a really nice metal to weld. And another feature is that I can sand this weld flush and it will become absolutely invisible. So this part could be polished and you wouldn't see the weld, or it could be chrome plated. Really some nice stuff to work with. And of course copper will never rust, so it's a beneficial material in that sense as well. So here's the copper joint after it's been sanded smooth. And I'm sure many of you are wondering what the application for this might be. Well, I'm holding this in front of a grill shell that I made from sheet bronze for a little pedal car. And I think you can see the corner on the bronze grill is absolutely beautiful. And this has been polished. Now, bronze is a different metal from copper. Bronze is actually a combination of tin and copper. And there's a bronze welding rod used to weld bronze sheet, but the process is very much like welding copper sheet. And with the bronze, as with the copper, once that weld seam is sanded smooth, it's absolutely invisible. The color match is perfect, welding copper with copper rod and welding bronze with bronze rod. Let's look at another application for bronze welding rod. Not only can you weld bronze with bronze filler rod, you can weld steel with silicon bronze filler rod. And there are some times when you might want to do that. To begin with, you need to understand that silicon bronze has roughly half the strength as steel, so it isn't a general purpose filler rod for steel. But in situations where you want to reduce the amount of distortion from welding, silicon bronze rod may help a lot with that. Or in situations where you need to build up a lot of weld bead, silicon bronze is very good for filling. Let's talk about the distortion in a little more depth. So I've welded two pieces together using silicon bronze filler rod, and by putting a straight edge on the bottom, you can see that I have very little distortion of the flat piece. Had I used steel filler rod for that application, there would be a great deal of distortion. So that's one of the situations where the silicon bronze rod is truly superior. You might want to experiment with this. Some of the most interesting and also the most demanding types of joints that I've had to work on are those of tubing, where you have complicated pieces of tubing that fit together. It's always a challenge to get a TIG torch into these tight little recessed areas, but it can be done, and I'll show you some of the techniques I use for that. In situations like this, the gas lens is going to be your best friend. And with the tungsten stuck out this far, we actually can get right into that little joint. The hand motions needed to make a joint like this really are quite complicated. The issue is the torch needs to follow a path so that the electrode is perpendicular to the joint everywhere along its path. A joint this long I would certainly do in sections. I probably would start from this point and weld along to this point. Then I'd need to stop and reposition my body and then get into a position where I can complete the rest of the weld. This is the most difficult joint configuration you're likely to encounter, but with some practice you can probably do a very nice job with this. The next thing we'll talk about is the importance of having a complete inert gas shield over the weld area. So I'm going to make a short weld with everything being done properly, and then we'll make another weld with not enough argon gas flowing, and you'll see a clear difference between them. So there's the weld with everything done properly. Now I'm going to make a change to the flow meter. I'm going to turn the flow meter from 18 cubic feet per hour down to about 9 cubic feet per hour. I'll make a second weld parallel to the first weld. Then we'll take a look at the difference. So let's take a nice close look at these two welds. So the weld made with enough argon flow is clean and shiny. The weld made with not enough argon flow is really, really dirty. This is something I had to learn the hard way. Even a tiny breeze will be enough to blow away the shielding argon gas, and you'll get contamination in the weld, just like the case where we didn't have enough flowing. So I've set the flow meter back to 18 cubic feet per hour, but as I'm making this weld, I'm going to turn on this little toy fan, and you'll see that it's just going to blow away the shielding gas. So I'll put the fan right over here, turn it on, and then I'll make a weld right next to our first weld. Okay, when you take a close look at this weld, you'll see it's even crummier looking than the one we did with 9 cubic feet per hour of argon flow. And this was done at 18 cubic feet per hour. I'm going to put just a thin stripe of oil on the metal, and then I'll make a weld that enters that oily area, and you'll see what happens to the weld, even though there's a full 18 cubic feet per hour of argon flowing. So here you can see what a hindrance oil is to having a TIG weld flow properly. Again, having the metal squeaky clean is essential for good TIG welding. For the next demonstration, I've intentionally stuck the tungsten electrode out way too far, and you'll see what effect this has on the weld. Even though I'm flowing a full 18 cubic feet per hour of argon, the weld area won't have a sufficient shield. I'll show you what I mean. So even though I had a full 18 cubic feet per hour of argon flowing, because the tungsten was extended so far, I didn't have proper shielding on this weld, and you can see this weld looks just as lousy as the previous three. So this shows the importance of having enough shielding gas in the weld area. Over the years, I found a couple more possible sources of weld contamination. Once in a blue moon, you might get a tank of argon that is contaminated. It's extremely rare, but in the 40 years I've been welding, it happened to me once, and it drove me nuts until I figured out what the problem was. So don't rule that out as a possibility if you're having consistent problems making a weld. Another thing that can happen is sometimes a little hole can be worn in the argon hose, and the hose acts like a carburetor, sucking oxygen or air into the argon gas, and that pollutes it. So check your system for leaks periodically. That can cause a problem too. And the next thing we'll talk about is electrode contamination. This will probably be your most frequent problem as you learn the process of welding. So I'm going to start a bead on this plate, and once I've gone about an inch, I will intentionally stick the filler rod against the tungsten, and we'll see what the results are. Oops, I've got a mess on my hands. And believe me, this is going to happen to you again and again as you start refining your technique of TIG welding. Let's take a close-up look at what the problem is. So you can see what a mess it makes of the weld area once that electrode gets contaminated. You can see the big black smudge around the weld. The problem is that when I touched the filler rod to the electrode, the filler rod actually melted and parts of it adhered to the tungsten electrode. And until I clean that off by sanding, I'm just not going to be able to make a nice weld. A lot of people try and kid themselves. They think, oh, I only contaminated the tungsten a little bit. I'll weld just a little bit farther. My advice, don't. If you have the slightest contamination, you're just not going to be able to make a nice weld bead. Stop, take the tungsten out, repoint it, and you'll be good to go. The next thing we'll talk about is heat control. And this is something you'll just have to learn through experience. It's pretty hard to give people the parameters for proper heat control. The good news is that with the TIG welder with the foot control, you have all the control you need with the foot pedal to give yourself the proper amount of heat. But it's only through experience that you learn how much heat is proper for a particular welding job. I'm going to run 3 beads on this piece of aluminum plate. I'm going to make the first bead with not enough heat. What you'll see is kind of a wormy little weld bead that stands up tall above the surface and doesn't flow into the base metal very well. The next weld will be nicely rounded, and you'll see that it does flow in nicely to the plate around it. And the last weld will be made with way too much heat. You'll see that the weld bead is very wide, and I'm probably going to get more sagging of the weld, so it's going to bleed through the backside a lot. Here we go. So the first weld, which is too cold, doesn't really flow into the base metal around it well at all. It's just like the bead is resting on top of the metal like a worm. So this is the characteristic of a weld bead made with not enough heat. This bead is just about right. It's nicely rounded. You can see distinct ripples in the weld bead, and it flows in nicely to the metal next to it. And this bead, where there was too much heat, doesn't have any definition of the weld bead at all, and it's almost flush with the metal. So, pretty good example of too little heat, just the right amount of heat, and too much heat. I want to talk a little bit about the hand technique used for TIG welding. The first thing we'll look at is the distance between the tungsten electrode and the workpiece. The ideal distance is right about 1/16 of an inch, maybe as much as 1/8 of an inch. If you're holding the tungsten closer than 1/16 of an inch to the weld puddle, you're probably going to dip it frequently, and of course that contaminates the electrode and makes it impossible to weld further. The problem with having the tungsten too far away is that the arc shape is a cone, so the farther you pull the tungsten away, the larger the arc cone is where it contacts the metal. That makes your weld puddle unnecessarily large. So you really need to carefully control the distance between the tungsten electrode and the workpiece as you're running the puddle across the metal. I'm going to make a weld 2 inches long. For the first 1 inch, I'll hold the tungsten at the proper distance from the metal, and then for the second inch, I'm going to hold the torch too far away. You'll be able to see the difference. Okay, so we'll take a close look at this, and you can clearly see that the first portion of the weld looks very nice. There's a well-defined bead, and in the area where I had the tungsten too far away, the bead has gotten much wider and it's flattened out, and there's not good definition of the weld bead itself. So that's the problem with holding the tungsten electrode too far from the metal. There's a problem with holding the filler rod too close to the electrode. If the welding rod is not withdrawn sufficiently, a big blob will form on the end of the rod. So you need to withdraw it enough that this doesn't happen. But it's also important that you not withdraw the welding rod too far. The end of the rod needs to remain within the argon gas shield. If you pull it outside of that shielded area, the hot end of the welding rod will oxidize. And then when you dip that oxidized rod into the puddle, you're bringing contamination into the weld. You'll see little black flecks around the weld area. That's an indication that this weld is contaminated. Let's do a couple of fun things now. First of all, let's weld a couple of razor blades together. Now, is this a practical application of welding? Well, I don't think so, but it is kind of fun, and you can amaze your friends. So it took a little figuring out for me to perfect the setup for this. What I've done is to put a couple of plates on my table that the back of the razor blades can rest against, and then I just use this plate to angle the tips together until they touch. That's the tricky part. And then it's really hard to start an arc on that narrow little edge. So what I've done is to put a block of metal right alongside the razor blades at both the beginning edge and the back edge, and that gives me a place to start the arc and end the arc. Here we go. Okay, there's our weld on a couple of razor blades. Let's pull that out and take a look. So if you ever need to weld razor blades together, now you know how to do it. Now we're going to weld some aluminum foil together. Now I measured this stuff and it's 1/1000th of an inch thick, and you might think it's absolutely impossible to weld. And this is kind of a parlor trick, but it can be done, and let me show you how. I'm going to lay one piece on top of another, and then I have a little fixture on my table here. This is just made from a couple of pieces of 1/8 inch thick material. So let me spread these apart, and we only want about 1/8 of an inch sticking up above the metal. The amount's not critical. And I'll put a clamp on this end. Now all we need to do is to start an arc here and just run it across as fast as we can. It could be AC or DC. It'll work either way. Here we go. And ladies and gentlemen, there is our weld on aluminum foil. Don't believe me? Let me show you. So you can see these are actually welded together quite strongly. So that's a wonderful trick you can show your friends. We've come to the end of our program on TIG welding. I'm sure you've come to appreciate how versatile a process it is. What comes along with the versatility, though, is the fact that it's a very demanding process to learn to do properly. I encourage you to experiment with different welding processes, and whenever you have the opportunity, it's great to watch other welders and talk with them about what they've learned about the TIG welding process. So I think you'll have a lot of fun as you learn to TIG weld, and you'll get a great deal of satisfaction once you learn to master the process of TIG welding.